And these are good questions. I mean, it's the difference between a mathematician and an engineer. It really is. A futures command is coming here, and I called up Dr. Woodkaiser and I said, you know, I do some applied stuff, and he's like, they want actually stuff you make. They want an engineer. So that's kind of the difference between, I guess I make apps, but I don't really do more than that. Okay, so again, this was the checkability theorem. I find this easier to work with just because you just go through a checkbox. If you have to prove something's a soup, you just go and check 1, check 2. There's a different definition. I don't know which one's going to be in the book that I'm using next semester, but this is called the epsilon definition. And it's a bit harder to understand. It's my highest viewed video. It's higher viewed than even my weight loss calculator video. Which is, you know, you would think that one got 200,000 hits on one day when we were in the New York Times, that calculator. So you would think that calculator would get more, but I guess there's needy math students that are worse off than people trying to lose weight. But yeah, I think this one's such a rough thing to understand. I'm going to do my best to explain it to you. But again, it's this idea that you're given an epsilon. If something, think about it as a limbo bar again. So you have this soup. It might not be in the set. But if you're given an epsilon and you subtract a tiny piece off that soup, there's got to be an x inside that range, no matter how much I dip, because it's the best possible limbo bar. So if I dip down, I'm going to find an epsilon that's in between the two. So if you look at this sequence again, and I give an epsilon equals 0.01, my little x is going to be 1. There's a 1, and then 0.99 would dip down below 1. It seems easy to understand with an example, but proving, this is the version that you need for that theorem that I just told you. I've used that theorem so many times to prove other things, that if I have a bounded, because a lot of times sequences don't need to have patterns. So they could have some wild looking thing. The Cantor set is a sequence that may not have a pattern, a set that may not have a pattern, but I know it has a sup and an inf. There's a theorem that says that. Once I know that inside the Cantor set there must be a subsequence that converges. So that's how you step around it.
So this is saying, like, if you have the sup of A, then chipping off like any amount of A will get you into.
If you take that limbo bar and lower it just a tiny bit, there's going to be a sequence member that's above it.
Does it have to be a sequence member? Because what if you're looking at like just like?
It has to be a sequence member.
It has to be a member of it.
Because think about it, if you had a max, an actual max, well, the max is going to do the job. In this case, it turned out to be the max. But if you had like something the reverse, if you just turn this as -1/n, turn it around. Now 0 is your soup. If I dip down a little bit below 0, any little bit, I'm going to find sequence members that are tucked in between. Because it was the limbo bar of the possible best max, not max, but soup.
Oh, it doesn't have to be equal to it.
It has to be above it.
Okay. Oh, that's cool. It doesn't have to be equal to that. Okay.
Got it? So again, I don't know if I'm going to prove Bolzano-Weierstrass stress. I want to get to Hilbert spaces as quickly as possible, just because I don't want to keep going on real analysis. It's not a real analysis class. You're just getting a potpourri of different topics. So I might have to let Bolzano-Weierstrass go to accommodate Hilbert spaces. But that is this is the definition you would use for Bolzano. Because if you're trying to prove a sequence converges, it's an epsilon definition. And this has an epsilon definition. And you have a candidate for a limit. So that's where you set it all up. And this is the one you use. If you try to use the checkability one, it won't work. Okay, infimums are the same with the inequalities reversed. So, maybe for your homework, I'll have you reverse all of them and give me the definitions. That's a good exercise. Okay, questions? If you take the random number generator on Excel, all those have to be fractions between 0 to 1. They're not supposed to have a pattern. They're pseudo-random though, but they do have a pattern, but it's not one that you can detect. You just plot those as n. You can do that right now. Just plot them. But just go up here and just instead of an, I put in equals rand. And then it go like this. It doesn't like that. Well, there you go. It's got a sup and an inf, and it doesn't have a pattern. But what's amazing about this is that I can pluck out of here a subsequence that does converge. That's goes on a bar stress. So when you're trying to prove something in general, you're not given anything about the set. You have no idea. You have to you have to cast your net out wide and think about all kinds of sequences. Like this is an example of a weird sequence that doesn't have a pattern, but it has a subsequence that converges. And there's a theorem that guarantees it to me, and it's those definitions I use.
What do you mean there's a sequence? That doesn't make sense.
So this is a sequence. I just plotted it, right? Inside this sequence is a subsequence of elements that will plot on and converge to the soup. I do so bad. You know what? Maybe I'll print out a proof of it for people. Yeah, maybe I'll print out. It's like it dawned on me this morning that I might not be doing it, and it made me really sad. But I like Hilbert spaces too, so another shiny object.